Throughout this course, there's been a few things that we've had to not really unlearn from previous years, but take a really big leap forward in terms of how we understand some of the things that we thought we understood. And we're going to do some more of that today. We're going to be talking about redox chemistry, which is a different way of looking at some reactions. So we'll talk about what all that means and why only some reactions in a moment. But if we took a few reactions, just sort of looked at them, not in terms of sort of the type of reaction that they are, but what else is going on. If I took these reactions, then you don't need to write these down unless you really want to, but these reactions all have something in common, even though we would identify them as different kinds of reactions. But the other kind of reaction that you've learned, at least one of the, depending on how you want to count them, we've also learned about double displacement reactions, and they are fundamentally different from those other three. So without spending a whole lot of time trying to dig into that, the bottom line is that the first three, those ones that had something in common, those are redox reactions. And with a redox reaction, and we'll talk about the history of that in a moment, but it comes, okay, we'll talk about the history of it now. It actually comes, the reduction part of it comes from the reduction and oxidation. But reduction is a term that came out of metallurgy, where if you took an ore, which would be a metal with something else, sulfur in this case oxygen, if you were to bring that down to just the metal, it would actually lose mass, because in this case the oxygen would be taken out, so its mass would be reduced. Whereas oxidation was more originally a reaction with oxygen, so turning back into rust. But now we've expanded that a little bit to say that other things happen. We're still going to use the terms oxidation and reduction, but they won't necessarily involve oxidation, and there won't necessarily be metals, metallurgy. So in a redox reaction, what you have is these elements that are going to have, or atoms are going to have, a particular oxidation state or an oxidation number. And if you change that, think of it like an ionic charge. If you change that, then it's a redox reaction. So if we think of it in terms of ionic charge, and it's going to apply to things that are not ionic bonds, so we'll have to tweak that a little bit, but it is a little bit like an ionic charge. So for example, in this synthesis reaction, sodium and chlorine both start out as neutral elements, and then when they react, we form this nice ionic bond where sodium is +1 and chlorine is -1. Well, what that means is that sodium has gone from a 0 to a +1, it's lost 1 electron, and chlorine has gone from a 0 to a -1. We've had this change in ionic charge, which we are now going to expand and call that a change in the oxidation state, or the oxidation number. So redox, what that means is reduction in its modern definition is a gain of electrons. And that sounds pretty weird because we're talking about reduction is somehow a gain, but we're hopefully used to these backwards things in chemistry. The reason why reduction is gain is because the oxidation number goes down. So for example, chlorine gained electrons, and its number, its ionic charge, went from 0 down to -1. That's the reduction part. It's a statement about its oxidation or number or ionic charge. Oxidation then is obviously the opposite, where I'm losing electrons, and that's going to mean the oxidation number goes up. So sodium went from 0 to +1, went to a higher oxidation number, and it did that by losing electrons. But again, it's going to take some time to get used to that backwards relationship, and then we're going to mess with it even more in a few minutes. So if I look at a number line as a list of oxidation numbers, oxidation means I'm moving more to the positive side, and reduction is moving more to the negative side. Now it's important to understand that it won't always start at 0, and it won't always go to minuses, or won't always go to positives. So for example, if I go from a +2 to a +1, well, I've gone toward the negative a little bit. That's reduction. If I go from +2 to +3, well, that's an oxidation. It doesn't have to start at 0. It doesn't have to go through 0. How do we get the oxidation number? Well, we already know what to do if it was ionic. So what we're going to do is we are going to, I don't want to say pretend, or we're going to treat everything as if it were ionic, or what would be true if it were ionic. We're not changing what we understand about ionic bonds and covalent bonds. What we're saying, though, is that for every for every combination of two atoms bonded together, one is going to be more electronegative, one is going to be less electronegative, and obviously there are a few that aren't like that, but for our purposes we're going to be dealing most of the time with combinations of different elements where one of them is going to be more electronegative. Well, that one we're going to assign it the negative oxidation state, and anything that's less electronegative, less pull on the electrons, we're going to assign it the positive. So if everything were ionic, that's how it would go, so that's what we're going to do. And which is just what I said, although I said it much longer. So this table is worthwhile. Now there's a couple of lines on here that are going to say exceptions. We're not going to deal with the exceptions, so you can leave those out. But this is going to be the basic starting point for almost everything that we do. Any element that is in an unreacted state automatically has an oxidation number of 0. And this makes sense because we would have known from before that sodium starts out at 0 and then it reacts and becomes +1. So anything that starts out before it's reacted has its full set of electrons. And that's true for things that are, say, diatomic as well. Monatomic ions, like a sodium ion, is going to have the ionic charge that it has. In other words, that ionic charge is also the oxidation number. Hydrogen, in almost every compound, for our purposes, every compound, hydrogen is always going to be assigned an oxidation state of +1. So if I look at water, if I look at hydrogen chloride, then hydrogen is always going to be a +1. There are some exceptions where it would actually be considered a -1. We're going to ignore those though, so we don't have to worry about it. Oxygen, in almost every case, for our purposes, every case, but almost every other case for real, oxygen is always going to be assigned an oxidation number of -2, much like its ionic charge is if it is with a metal. But even when it's bonded with other nonmetals, it doesn't have an ionic charge, but it would have an oxidation number of -2. There are a few exceptions which don't matter to us, but there are some exceptions where oxygen actually behaves as a -1. If you're wondering how do we know about those exceptions, you don't need to. So we won't. So how do we use that? Well, one of the things is to use that information to figure out ones that aren't on that list, because the periodic table is pretty large and this only covered a few of them. So if, for example, I gave you this, well, there's carbon, hydrogen, oxygen. I know something about hydrogen, I know something about oxygen. I don't know anything about carbon, so I use that. The other thing I know is that the entire thing is a neutral compound because there's no ionic charge written beside it. So what that means is the oxidation numbers, remember those are the stand-in for ionic charges, add up to 0, neutral. So I start with carbon, don't know. I start with hydrogen, I do know. I start with oxygen, I do know. How do I know it's not an exception? Because I'm not going to give you the exceptions. That's how. And then I know my net charge is 0 because overall the net ionic charge and the sum of the oxidation numbers are going to be the same. So I can use that information to solve for the unknown of carbon, which I identified as X. In this case, carbon has an oxidation state of -2. If I have an ion, something that's an overall ionic charge, exactly the same thing actually. I don't know enough about chromium. I do know everything I need to know about oxygen, and I do know that by the time all of that stuff gets together, there's an overall -2 charge on that ion, which means I can do exactly the same math and solve for the oxidation number of chromium, which in this case is +6. What if there were 2 chromiums? Same thing. What if there were more than that? Same thing. Except in that case it wouldn't be just 1x, it would be a 2x or some other x. Okay, I said I was going to mess with your understanding of oxidation state and reduction coming up. This one is going to be logical when you think about it, but it's going to get in the way. So bear with, buckle up. What we know already is that oxidation is a loss of electrons and reduction is gain of electrons. Too easy, getting used to that. Might take me a minute to identify which one has happened, or if I was given a reaction, asked you which one got oxidized, which one went through reduction. Here's the thing though. I can also talk about an oxidizing agent. Now an agent is a thing that causes it to happen. So an oxidizing agent is a thing that causes oxidation. Oxidation is a loss of electrons. So how do you cause oxidation? You take electrons away. Well, if I take electrons away, I have effectively gained them. That means I got reduced. And a reducing agent is the thing that causes reduction. Well, if reduction is the gain of electrons, I could be a reducing agent and stuff electrons onto something else. I've lost electrons. So there really is that a second backwards relationship in that an oxidizing agent causes oxidation, but it gets reduced. There's a bit more of a nuanced meaning than that, but we'll come back to that another time. Okay, that wasn't real long, hopefully. It depends on what I edit. But these are the things we should be able to do at this point. I should be able to identify whether or not something has been a redox reaction. Biggest clue is something an element on one side and a product and in a compound on the other side? Doesn't matter which side is which, but as soon as I see that has happened, it is automatically going to be a redox reaction. After that, I might have to look a little bit more carefully, identify what's been oxidized, what's been reduced, and figure out oxidation numbers on some things. And then after that, we're just going to get some more practice with this stuff, and then we'll build on it again. Talk to you later.